so let's try Kyber. Now, Kyber is the recommended post-quantum encryption scheme. So this is the one we're supposed to actually understand. Unfortunately, it's pretty confusing, and the first half of here is just mathematics. So you need these quantities. Remember, in RSA, you need P and Q and a few other things. These are the quantities you need in Kyber. You need a vector of polynomials with small coefficients, S, that's the private key. Then Q is a modulus, which is just a prime number. F is the polynomial modulus, which is x to the fourth plus 1, and x is a variable that's going to come up later. A is a matrix of random polynomials, and that's part of the public key. In fact, the public key, and T is a calculated vector, and the public key is A and T. And E is a vector of small random error values. So you have all these quantities. So to make the private key, you just choose random small coefficients. So in this case, we're just going to use plus and minus 1. They call this baby Kyber, just like the RSA we did a few projects ago where we used really small prime numbers for RSA, so it was not secure, but we could see how it worked. This is using really small numbers for Kyber, so you can see how it works. So in this case, to make small coefficients, we're just going to use plus and minus 1. So minus x cubed, minus x squared, plus x, minus x cubed, minus x. This is a vector containing two polynomials with small coefficients, either plus or minus 1. So now we generate the public key. We choose a prime number like 17 to be the modulus. And now you generate a matrix of random polynomials. These are just random numbers modulus q. So they're going to be from 0 to 16. So you just have 4 random polynomials, as you see here. And that's A. Now you choose some errors, which are again small, so the coefficients are 1 or minus 1. And now you take A times the S that you generated up here. S was just random small numbers. A was just random numbers entirely. You multiply them together and add the error, and that gives you this thing called T. And the way you do matrix multiplication is you take the element in the top left here and multiply it by the top thing here, and then add this top here, and that'll give you the top term. So the top term is this mess. And now you multiply them out and get these quantities, x to the 6th, x to the 5th, x to the 4th, and so on. And now you use the fact that x to the 4th is always minus 1, because we have this modulus. So this x to the 6th turns into minus x squared. This x to the 5th turns into minus x. The rest, this x to the 4th, just as minus 1. So now you simplify it, and you'll end up with a polynomial of order 3. So that's how you get the top term. Then you do the bottom term, you get another polynomial of order 3. So the end result is this. This is T. That's the calculation. And now the public key is AT, where this is A, which you just chose random numbers, and this is T, which you calculated. And the private key is here. That's the game. So that's how you calculate the public and private key, and you can do it yourself without a computer this way. All right. Now, then you can do it, of course, in Python. And this should work fine in Google Colab, and I think I've got it all set up already in Google Colab in my other tab here. Okay, if I reconnect and it hasn't forgotten, all right, so here we go. So you download the Kyber Python library and move it into your local directory as kyber.py. This is a way to get it in there. Once again, this is new, so the libraries aren't that easy to find, but I just prepared it and put it on my webpage. You can download it. So you have a Kyber. Now you set your parameters. So this is the modulus, which is just a prime number, and we're going to use 17. Here's the F. This is x to the 4th plus 1. That's what this means. The first term is the number, a coefficient of x to the 4th, then x cubed, x squared, x, and 1. So this 1001 is the F polymodulus. Here's S, which is small coefficients. So like I say, we just have plus 1 and minus 1. And this is the secret key that we, the same as before, minus x cubed, minus x squared, plus x. So it's no x to the 4th. I think this one is backwards for some reason. And minus x cubed minus x, minus x cubed minus x squared plus x plus 0. You read this one right to left. For some reason it's set up that way in the library here. And here's the other one. The second part of it is minus x cubed minus x. So this is x cubed, x squared, x to the 1, and x to the 0, right? So that's what it is. You read them right to left for some reason. And here's the same structure of the random numbers for the A. And here's the error, which has to just be small numbers, 1 or minus 1 or 0. That's the noise. So now you can do add vector, a matrix multiplication of A times S, where the modulus for the polynomial is F, and the modulus for the coefficients is Q. So there are 4 parameters. And then you add it to this other quantity, which is the error, and the modulus Q. So that's what this mesh does. The add vector and multiply vector are part of the library of Kyber. And so that will give you the answer. And so this is going to be 161507. Let me check my original one here. And it had the answer, which was, it's 161507, which is there, 161507. It's these coefficients when red, right to left. You can see it's getting the right answer in a simple format. So this is how you calculate t. And now that you have all those parameters, you can now send a message. So you choose your message, and the message we're going to send is 1101. The message is also a polynomial, and in this simple case, we're just going to send a message of a few bits. And so you have a vector, and you add noise, and you go through these calculations, and you'll end up with an encrypted message here. So the encrypted message is this mess, several polynomials, and the decrypted message gets you back to 1101. So it is a little baffling, but so is RSA at first, and we need to get used to this. This is the sort of operations and parameters you use for lattice encryption. And let me go to my instructions and see if there's anything here that's going to explain it more helpfully, but I think not. All right, so there's the encryption and decryption process. And then there's decryption. All right, and I think that's it. Yep. All right, and that's all I wanted to show you. This did encryption, decryption, and this I was doing decryption again. Maybe I did the same thing twice here. Anyway, that's what I wanted to show you. At first, you're just manipulating things without understanding them, but with practice, you get a little more used to it, and gradually we're all going to have to get used to this. This is going to be the standard to replace RSA and elliptic curves. We'll all be learning to do this. Although we'll probably just do the second half where you use these libraries, and probably libraries will appear that make this easier, that conceal more of this complexity from you. But this is what's really going on behind the scenes. So I'm going to stop this one.